Good morning everyone. In our discussion on numerical solution of ordinary differential equations, all along we were concerned with the numerical solution of initial value problems governed by first order ordinary differential equations of the form dy by dx is equal to f of x comma y subject to some initial condition y of x naught equal to y naught. We now move on to the boundary value problems which are governed by second order ordinary differential equations along with boundary conditions which are specified at the end points of a closed interval. So, our goal is to develop numerical techniques for approximating the solution of 2-point boundary value problems. They are in general written in the form y double prime equal to f of x y y prime. Here y is the unknown function, it is a function of x, prime denotes derivative with respect to x, and here f is an arbitrary function of 3 of its arguments x, y and y prime. This differential equation is defined in the interval a b, which is a closed interval, and y also satisfies the boundary conditions, namely the boundary conditions are of the form alpha 1 y at a plus alpha 2 into y prime at a is alpha 3, beta 1 y at b plus beta 2 y prime at b equal to beta 3. Here alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 are constants which are known to us because the boundary conditions are prescribed. And if the right hand side function f is such that it is of the form p of x into y prime plus q of x into y plus r of x for some functions p, q and r, then we say that the boundary value problem is a linear boundary value problem and it is governed by the second order differential equation y double prime is equal to p of x into y prime plus q of x into y plus r of x along with the boundary conditions which are given here. If it is not of this form, then we say that the boundary value problem is a non-linear boundary value problem. Now, we would like to understand these boundary conditions. We observe that we have a linear combination of the unknown function at one end point and its derivative at that end point is prescribed as alpha 3 in the first boundary condition. And in the second boundary condition, similarly we have a linear combination of the function value and its derivative at the other end point b is prescribed and it is given as beta 3. So, such type of boundary conditions are known as Robin or mixed boundary conditions. There are special cases. If suppose alpha 2 is 0 and beta 2 is 0, let us see what it means. If alpha 2 is 0 and beta 2 is 0, then we have alpha 1 into y of a is alpha 3 or y of a is alpha 3 by alpha 1 and beta 1 y of b equal to beta 3. So, y of b is beta 3 by beta 1. So, in the special case when alpha 2 and beta 2 are 0, then the boundary conditions given above reduce to conditions of the form y of a equal to alpha and y of b equal to beta, where alpha and beta are given to us. Such types of boundary conditions are called Dirichlet boundary conditions. So, by a Dirichlet boundary condition we mean the unknown function is specified at the end points of the interval a b in which the differential equation is satisfied. Then there is another special case where alpha 1 is 0 and beta 1 is 0. Let us see this case. If alpha 1 is 0 and beta 1 is 0, then we have boundary conditions which are given only in terms of the derivative of the unknown at the two endpoints A and B. So, in this case the boundary conditions are of the form y prime at A is some gamma and y prime at B is delta. So, the conditions are given in terms of the derivative of the function at the boundary points, namely A and B. Then such types of boundary conditions are called Neumann boundary conditions. So, a boundary value problem governed by the second order differential equation subject to boundary conditions which are of the Robin type or of the Dirichlet type or of the Neumann type will be given to us, and we now try to develop numerical methods for solving any of these boundary value problems using finite difference method. So, let us try to understand this finite difference method and see how we can apply the finite difference scheme for solving boundary value problems which are linear boundary value problems. So, we consider the general second order one dimensional 2-point boundary value problem, namely y double prime is f of x y y prime, which is defined for x in the interval a b along with this Robin type of boundary conditions. So, as we said, we would like to understand finite difference method of solving linear boundary value problems subject to the boundary conditions which are specified in this form. And we focus our attention on the linear boundary value problem, and so the right hand side f is of the form p of x into y prime plus q of x into y plus r of x, where x lies between a and b. So, this is our second order differential equation, and let us first focus on the case when we are given Dirichlet type of boundary conditions, namely the unknowns are prescribed at the two endpoints A and B. So, the conditions are y of A is alpha and y at B is beta. So, the question is solve this boundary value problem subject to Dirichlet boundary conditions using a finite difference method. So, what is the objective of a finite difference method? The objective is that here we approximate the value of the exact solution to the boundary value problem y of x at a set of points, namely x naught, x1, etc., xn, which belong to the interval a b where the differential equation is defined. So, this interval a b is one in which the differential equation is defined, and we select points x naught, x1, etc., xn in this interval and try to get the approximate solution at these discrete points. That is what will be obtained using finite difference method. So, to do that, let us denote by yi the value of the exact solution at the point x is equal to xi, and let us denote by wi the finite difference approximation to this exact value, which is yi at any point xi. So, what do we do in finite difference method? We are given a second order differential equation satisfied in an interval. So, we try to replace each of the derivatives which appear in the differential equation by appropriate finite difference formula. And I recall the finite difference formulas which we have developed in our discussion on numerical differentiation. So, we already know how to approximate the derivatives by means of finite difference approximations. So, for example, if a second order derivative appears in the differential equation, you can replace this second derivative y double dashed of xi by a second order accurate finite difference formula, which is a central difference formula given by this, and the error is of order of h square. And if there appears a first order derivative in the differential equation, then replace that again by a second order accurate finite difference formula, and the order of this method is 2 and the error is of order of h square. So, you replace the derivatives which appear in the linear boundary value problem governed by the second order equation, which has the second order derivative and the first order derivative by means of these finite difference approximations. Then what happens? As a result of this, you will see that when you replace the derivatives by appropriate finite difference approximations, then that single continuous differential equation for the unknown y of x is reduced to a system of algebraic equations for the unknowns w naught, w1, w2, etc., wn, which are values at the points x naught, x1, etc., xn, and these are approximate solutions of this differential equation or the boundary value problem. So, let us understand how we can do it. What is step 1? Step 1 will be to get these points x naught, x1, etc., xn at which we seek approximate solution of the differential equation. So, how do we get these points? We take the interval AB, we partition this interval into number of sub intervals by means of points x naught, x1, x2, etc., xn, such that they satisfy this condition. So, for simplicity, we assume a uniform grid. What does that mean? We choose these points x naught, x1, etc., xn in such a way that they are equally spaced. So, how do we get it? We divide the interval AB into subintervals of equal width h. What is the step size h? The step size h will be xn minus x naught divided by capital N if we want to divide the interval AB into n equal subintervals. So, our step size h will be xn minus x naught by n. So, our points xi which appear in the interval are of the form x naught plus IH. So, the distance between any two successive points is going to be h, which is b minus a divided by n. So, having chosen these points, these are the points which are referred to as grid points. The end points a and b, where a is x naught and b is xn, they are called the boundary grid points. On the other hand, the other points which are x naught, x1, x2, etc., xn minus 1, which appear in the interior, they are referred to as interior grid points. At each of these points xi, the solution, the exact solution is y of xi, which we denote by y suffix I, and approximation to this exact solution yi are denoted by wi. Wi is an approximation to the exact solution at the point xi, namely it is an approximation to the exact solution y of xi, which we denote by yi. And what is this h? H is the step size or the mesh size, and h plays a vital role, namely it is a key parameter which governs the accuracy of the finite difference method. So, what is the next step? Having partitioned the interval and obtained the points at which we seek approximate solution, we move on to getting what is known as the algebraic system from the finite difference equations. So, let us understand how we do this. So, we take the given differential equation which describes this boundary value problem, and our focus is going to be on linear boundary value problems. So, our differential equation is of the form y double prime equal to p of x into y prime plus q of x into y plus r of x. So, we evaluate, we know that the differential equation is satisfied at each point x in the interval a b. So, we evaluate the differential equation at each of the interior points that we have chosen in the interval a b. What are those interior points? x1, x2, etc., xn minus 1. So, we have y double prime evaluated at xi will be p at xi into y prime at xi plus q of xi into y at xi plus r of xi, and this is for I is equal to 1 to n minus 1. The differential equation is satisfied in the interior of the interval is reflected here. Now, what is p of xi? Let us denote it by pi. It is just a notation. Q of xi is qi and r of xi is ri. Since the differential equation is given to us, we know what are p of x, q of x, r of x, and therefore, we know what are pi, qi and ri at each of the I, which is 1, 2, 3 up to n minus 1. So, we use the notation and write down this step as y double prime at I is pi into y prime at I plus qi into y at I plus ri for I is equal to 1 to n minus 1. What is the next step? What did we say? Our goal in finite difference method is to replace each derivative that appears in the differential equation by an appropriate finite difference formula. So, we replace now the second order derivative, the first order derivative by appropriate finite difference formulas. In what follows, we shall consider the second order accurate central difference formula for replacing the second order derivative and the first order derivative which appear in the differential equation governing the boundary value problem. So, what is y double prime I? Finite difference formula for y double prime I is that it is yi plus 1 minus 2 yi plus yi minus 1 by h square, and the method is of order 2. So, the error is of order of h square, and that is equal to pi into y prime I. So, again we replace the first derivative by second order accurate finite difference scheme, which is the central difference formula. So, it is yi plus 1 minus yi minus 1 by 2h plus qi into yi plus ri, right, plus here this is a second order method. So, plus order of h square. So, now I drop the truncation error term. So, when I drop the truncation error term, I have to replace all these exact values at xi by the corresponding approximate values. As a result, I will get the scheme to be wi plus 1 minus 2 wi plus wi minus 1 by h square, and that is equal to pi into wi plus 1 minus wi minus 1 by 2h plus qi into wi plus ri, and this is satisfied for all I, which is 1, 2, 3 etc. up to n minus 1. So, this will give us n minus 1 equations in the unknowns wi. In addition, there will also be w naught and wn appearing here. When will that come? When I is equal to 1, see you have a I minus 1, so that will give you w naught. And when I is equal to n minus 1, when you substitute it here, for that you get w n minus 1 plus 1, and that is wn. So, you will also have w naught and wn appearing when I is 1 and I is n minus 1 respectively. So, totally there will be n plus 1 unknowns, namely w naught, w1 etc. wn. But we have not made use of the boundary conditions which are given to us so far. So, this is the time that we make use of these boundary conditions. Let us see what it gives us. So, we use the Dirichlet boundary conditions. The first condition is the unknown y is specified at one end point, namely the left end point A. What is it? Y of A is alpha, and A is our x naught. So, y of x naught is alpha. Y of x naught is denoted by y naught. So, y naught is alpha, And how do we denote the approximation to this in our notation? It is W naught. So, W naught equal to alpha, and alpha is prescribed. So, we know what W naught is. Similarly, y at b, the other endpoint, is prescribed to be beta. So, y at xn is beta. In our notations, it is y suffix n, and that is beta. And how do we denote this approximate value at xn? Or in our notation says that it is Wn. So, Wn is beta, and beta is prescribed. So, we also know Wn. So, from the boundary conditions, we are able to get W naught equal to alpha and Wn is equal to beta. So, we now have a numerical method of second order. Why second order? Because we have replaced the derivatives which appear in the differential equation by a second order accurate central difference formula. So, we have a numerical scheme which is of second order, and the scheme is Wi plus 1 minus 2 Wi plus Wi minus 1 by h square is Pi into Wi plus 1 minus Wi minus 1 by 2h plus Qi Wi plus Ri, and this is true for I is equal to 1 to n minus 1, and we are, in addition we have W naught equal to alpha and Wn is equal to beta, with the help of which we can solve for the n minus 1 unknowns W1, W2, etc., Wn minus 1. So, we would like to rewrite these equations in such a way that we can put them in a matrix form, say AW equal to B, where A is an n minus 1 cross n minus 1 matrix, W is an n minus 1 cross 1 vector, and B is an n minus 1 cross 1 vector. Let us see whether this is possible. So, to do that, we multiply this equation star by minus h square and collect the like terms, namely what are the coefficients of Wi minus 1, what are the coefficients of Wi, and the coefficients of Wi plus 1. So, we collect these terms and then write them in a systematic way, so that when we take values I as 1, 2, 3, etc. up to n minus 1, this will give n minus 1 algebraic equations in n minus 1 unknowns. Why do we multiply by minus h square and collect the terms? The multiplication of this by minus h square, so, will result in the coefficient of Wi to be positive. In addition, it will help us to avoid division by a small number. That is why we multiply the entire equation by minus h square, and then we collect the like terms. And we observe that if we collect Wi minus 1 coefficient, so I have multiplied by minus h square, so this will have a negative sign, so I have a minus 1. There also appears Wi minus 1 here. So, when I multiply by minus h square, this will become positive, but I take this term to the other side, and so this will have coefficient minus h by 2. Why? This is multiplied by minus h square. So, h square by 2h, that will give you h by 2. It goes to this side, and therefore, I have a minus h by 2. So, the coefficient of Wi minus 1 is minus 1 minus h by 2 into Pi, namely the coefficient which appears here. These are all the terms with Wi minus 1 in this equation. Now, I move to coefficient of Wi. I have multiplied by minus h square. So, this coefficient will be plus 2, that appears here, and I have a Wi here. I multiplied by minus h square. So, the term is minus h square Qi, but I take it to this side. So, that becomes plus h square into Qi. So, coefficient of Wi is 2 plus h square into Qi. Then I collect coefficient of Wi plus 1. So, here I have minus 1 as the coefficient, and from here it is going to be plus h by 2 into Pi, and that is what I have written here. So, we have collected the like terms, and what will appear on the right hand side? I have multiplied by minus h square. So, minus h square r I will appear on the right hand side. So, this gives us the equations in the algebraic system for the unknowns W1, W2, etc., Wn minus 1. So, if I substitute I as 1, we already had seen this. When I substitute I as 1, this turns out to be W naught, and I know what W naught is. It is equal to alpha. So, I make use of that and rewrite this equation when I is equal to 1 as follows. So, this is the equation when I take I is equal to 1 and I use the fact that W naught is alpha. So, that leads to the equation in the unknowns W1 and W2 as this. Similarly, when I is equal to n minus 1, we have seen that this will give you Wn, and Wn is prescribed to be beta. And so, I can make use of that information here and take this term to the right hand side. So, when you do that, you end up with an equation in the unknowns Wn minus 2 and Wn minus 1. The term with Wn goes to the right hand side, and we have used the fact that Wn is beta. So, for I is equal to 1, this will be the equation. For I is equal to n minus 1, this will be the equation, and so we write down the system of equations in the form A into W equal to B. Let us denote the elements in A as follows. The elements which appear on the diagonal are denoted by Di. The elements which lie above the diagonal are denoted by Ui, and the entries which lie below the diagonal are denoted by Li. What is the unknown vector? W, and it has components W1 to Wn minus 1. What is the right hand side vector? It is B. It has components B1, B2, etc., Bn minus 1, and they are written here. So, we have a system of the form A into W equal to B. Let us now give the expression for Di, Ui and Li, which are obtained from the equations which we have derived. So, Di is the coefficient of Wi. So, it is 2 plus h square Qi. Ui is the coefficient of Wi plus 1. So, it is minus 1 plus h by 2 Pi, and Li are the coefficients of Wi minus 1. So, Li is minus 1 minus h by 2 into Pi. So, for I is equal to 1, 2, 3 up to n minus 1, the entries Di, Ui, Li can be obtained from here. So, I have again written down the right hand side vector B. So, we have now a system of equations of the form AW equal to B. So, we now see that when we replace each of the derivatives that appear in the second order differential equation which governs the boundary value problem along with the boundary conditions, the single continuous equation for the unknown y of x is reduced to a system of algebraic equations which can be put in matrix form AW equal to B. So, what is it that we need to do? We have to solve this system. When we solve this system, we will end up with those unknown values W1 to Wn minus 1, which give us the approximations to the exact solutions y of xi, where xi are the interior points in the interval, which we have selected by dividing the interval into equal number of subintervals. Before that, we need to answer a question. What is that? What can you say about the solution of the system? Is the solution a unique solution? Yes, under certain conditions we can show that the system possesses a unique solution. So, let us look into all those conditions. Suppose that this function p is a continuous function and this q is such that q of x is greater than or equal to 0 for every x in this interval a b. So, let us start with this condition. Then the continuity of p on this closed interval a b guarantees the existence of a positive constant L such that mod p of x will be less than or equal to L for on the interval a b, and this is by extreme value theorem. So, I choose my step size h to be less than 2 by L. What is the step size h? We divide the interval a b into n equal subintervals by means of points xi such that h will be b minus a divided by capital N. So, we choose our step size h in such a way that h is less than 2 by L, where L is such that modulus of p of x is less than or equal to L on the interval a b in which the differential equation is defined. Then what happens for each value of I, h by 2 into pi will be less than 1. Why? H by 2 into capital L is less than 1. So, h by 2 into pi will be less than 1 and it will be greater than minus 1. What does that imply? Let us look at minus 1 minus h by 2 into pi and minus 1 plus h by 2 into pi, which appear in the system a w equal to b as Li and ui. So, let us find out what is the sign of these terms. Since h by 2 pi lies between minus 1 and 1, these will be always negative, and therefore, the absolute value of minus 1 minus h by 2 pi is 1 plus h by 2 pi, and absolute value of minus 1 plus h by 2 pi is 1 minus h by 2 into pi. Now, let us consider rows 2 to n minus 2 in the system a w equal to b. These are the absolute values of the off diagonal entries. So, let us consider the sum of the absolute value of the off diagonal entries, namely modulus of minus 1 minus h by 2 pi plus modulus of minus 1 plus h by 2 pi. So, that turns out to be 2, and that is less than or equal to 2 plus h square qi in absolute value. What is this? This is the diagonal entry di in that row. So, what have we shown? For all the rows I from row 2 to row n minus 2, modulus of Li plus modulus of ui is less than or equal to modulus of di. That is, sum of the absolute values of the off diagonal entries is less than or equal to the absolute value of the diagonal entry. Let us see the rows 1 and n. Now, in row 1, we have modulus of u1 to be modulus of minus 1 plus h by 2 p1, which is 1 minus h by 2 p1, and mod d1 is modulus of 2 plus h square q1, and so it is this. And we observe that mod u1 is strictly less than mod d1. Similarly, in the n minus 1th row, mod un minus 1 is this, and mod dn minus 1 is 2 plus h square qn minus 1, and we observe that mod un minus 1 is strictly less than mod dn minus 1. So, what does it say? It says that the diagonal entries in the matrix A are such that the absolute value of the diagonal entry from row 2 to row n minus 2 is greater than or equal to sum of the absolute values of the off diagonal entries in that particular row. This happens in each row from row 2 to row n minus 2. And in row 1 and row n minus 1, there is strict diagonal dominance. A is a diagonally dominant matrix, and therefore A is non-singular. So, A inverse exists and therefore, the system AW equal to B has a unique solution given by W equal to A inverse B, and this is what we wanted to find out, whether the system has a unique solution. Yes, it has a unique solution under the conditions that P of x is a continuous function on the closed interval and Q of x is greater than or equal to 0 on the interval AB, and the step size h is less than 2 by L, where L is such that modulus of P of x is less than or equal to L for x belonging to the interval AB. So, the conditions given above are sufficient to guarantee a unique solution of the system, provided the step size h satisfies the condition that h is less than 2 by L. Now that we know that the system has a unique solution, the only step that remains to be done is solve this system and obtain an approximate solution. We will continue this in the next class.